Hello and welcome back to section 2.3 product and quotient rules and higher order derivatives. We're going to finish up the examples for this section. And so this example number 6, is actually a really good example about how do we determine when we're going to use a product rule or a quotient rule or some stuff like that. So if I look at this first one, I have y equals x squared plus 3x all over 6. It looks like it's going to be a quotient rule, but actually I'm going to rewrite this problem so I don't have to do a quotient rule. And I would highly recommend that if you can rewrite the problem correctly and so you don't have to do a quotient rule, then your life will be much better. Now it kind of even looks like a product rule, but since this 1/6 is a constant multiple, I just leave that out of the problem, and then I just go ahead and leave it out of the problem, and then I can just take the derivative of the thing with the x's, and that's the expression with the x's, and so that's where we're headed, so we don't have to worry about this. So when I do my y prime, I'm going to get 1/6 times. Now I can take the derivative of this thing, which is, since it's a polynomial, I can just take the derivative of each part and add them together, which gives me something that looks like this. Now if I wanted to make it look a little bit more like the way it started, I could write it all over 6, or I could distribute the 1/6 to each one of these, and so maybe I might use y prime is equal to 1/3 x plus 1/2. That might be a way to write it, or something like that, since I'm not going to get a common denominator. And so that's what we're talking about when we're doing these. So then the next one, same idea. Do I need to do a quotient rule? Well, no, I do not, because in this case, 5/8 is just a fraction, just a constant multiple again. And so 5/8 times x to the 4th means that the 5/8 can be left alone when I take the derivative. So dy dx will equal, when I take the derivative of this, the 5/8 stays as it is, and I just get a nice little power rule, which is 4x cubed. And so then just a quick little simplification, I will get my dy dx to be 20 over 8, which actually can be reduced to what is it, 5 over 2 x cubed. And so that's basically my best simplification for that problem. That now when we look at something like this, yeah, you'll notice that I'm going to have to do a quotient rule on this. Or actually, I don't need to. I could do a quotient rule on it because I have an x on the top and the bottom. But since every term pretty much has an x in it, I can actually divide both of these terms by x, and it'll actually make my life a little bit easier. So I'm going to do some math and distribute this thing and try to rewrite this a little bit. So I'm going to say y is equal to negative 9x plus 6x squared all over 7x. And so now if I divide everything by 7x, you can see that my new problem would be y equals negative 9/7. The x's cancel out, and then over here it's going to be plus 6/7 x. So now I have a much simpler problem to take the derivative of, and so when I take the derivative of that, y prime is going to equal, well, this is 0 because it's a constant, and so then I would end up with just the derivative of this would be 6/7 x to the first. Well, I'll multiply by the 1 and reduce the power, means that my final answer for this is going to be 6/7. So rewriting these is definitely to your advantage. The next one I'm going to want to rewrite also, and remember that the 9/5 is a constant multiple, but I don't like the x squared on the bottom. I don't have to do a quotient rule because there's no x on the top, and I'm going to write this as x to the negative 2, which means I'm back to my power rule at the very beginning. So y prime will be, well, if I leave my 9/5 alone, multiply by the old power and reduce the power by 1. Now be careful, most people go to negative 1, but it's actually negative 3. And so at this point, y prime will equal negative 18/5 all over x with x cubed on the bottom. Or I could have left it as x to the negative 3. It doesn't really matter, but that's my final answer for this one. So sometimes it's to our advantage to do a quotient rule. Sometimes so it's on you to kind of figure out where we're going and what's the easiest plan of attack for this. So then the next one, I'm going to have to find the derivative of each one of these functions. And sometimes I need to do, this is basically just trying to remind us our trig functions, and if you are looking in your book, you need to know the trig functions that are on page 123. So you need to know page 123, those are the trig functions. Make sure you get them because you will be using them all year. And we'll talk about them in class also. But anyway, so our trig function, when we go through and do the derivative of this, well, this is like a polynomial, so I can do the derivative of each one separately. So I can say y prime, when I take the derivative of x, is 1. And now when I go to tangent, I have to remember my rule, and the derivative of tangent goes to secant squared. So I get something that looks like that, and that's my final answer. That's the best we're going to get for this one. For the next one, you'll notice I'm taking x times secant, and when I multiply x times secant, this ends up giving me a product rule. And so a quick refresher of our product rule is that we do f prime of x, g of x, plus f of x, g prime of x. And so that's basically what I'm getting there. And so I'm going to say f of x is my x value, g of x is my secant of x. And so when I go ahead and take the derivative of this, I just follow this rule because it's a product rule. And so y prime will give me the derivative of x is 1. And so I leave secant x alone. And then I add on the f of x, which is x, and then I take the derivative of secant x, which happens to be secant x tangent x. Now I can simplify this a little bit by taking y prime and factoring out a secant x, and it's more just a matter of how the preference you want it to look like. So I'm going to say 1 plus x tangent x would be my final answer. And it doesn't really matter. You could write it either way. It just kind of depends on the form of the question and how the answer wants it written. So I would take either of them. So then we're going to go ahead and differentiate both sides of this and see if we can get to the same spot, because one of them looks like a product rule and one of them doesn't. So or a quotient rule and one doesn't. So just a quick reminder on the quotient rule. Remember, it's f prime of x, g of x, minus f of x, g prime of x, all over g of x squared. So that's our quotient rule, so that's what I'm going to need to do for this first one. And so when I go through and say y prime, I'm going to take the derivative of this. Well, the derivative of 1 is 0, and the derivative of cosine would go to negative sign, but since it's already negative, I'm going to write it as sine of x. So there's my f of x. Remember, the f of x is the top part, and the g of x is the bottom part. So sine of x times sine of x. And then I get to subtract away the leaving the top alone, so I get 1 minus cosine x, and then when I take the derivative of the bottom, I get another cosine x. All of this is over sine of x squared. Now, I don't have to write parentheses and put the square out there. I could put the little 2 between the sine and the x, and that's what I'll do on my next one. But I'm going to do a little bit of simplification, so I get sine squared x minus 1 plus cosine squared x. And then on the bottom down here, I have sine x, sine squared x. Now, I cannot cancel out sine squared x top and bottom like that, because that just becomes poor math when we do this. And what you'll notice, though, is that we have one of our Pythagorean identities, sine squared x plus cosine squared x. And so if I get those put together, oops, I misdistributed here. I needed to distribute, so I did that wrong up there. Sorry. So I just changed the signs on the first one, and I forgot to multiply by a negative cosine of x. So sorry, I was doing the problem wrong, but you're probably yelling at me, saying, "Come on, you're doing it wrong." Sorry about that. So that's what I should have on top. And so this guy right here, what I circled, goes back to my Pythagorean identity, is that I end up with sine squared x plus cosine squared x is 1. So what I circled is now 1. I'm going to write it in red. I have my subtract 1 that was originally there, and then I forgot my subtract cosine of x, which is what I just remembered when I needed to distribute to both of them, and that's what I should have gotten here. And actually, that 1 would not be, that 1 in the, oh man, that 1 right down here would not be in existence because I did my math wrong. So that 1 right there is gone. So sorry, hopefully I'm not confusing you too much on this. I probably am, but hopefully I'm not. So then I'm going to do a little more simplification on this. Sine squared of x can be written well, actually, I could just divide both of these guys. Since I've got 1 minus cosine squared x, this could be written as 1 over sine squared x minus cosine x over sine x times 1 over sine x. So just using the properties, since I'm subtracting here, I can break them apart. So 1 over sine x, I believe, is cosecant squared x. Sine over cosine over sine is cotangent x, and 1 over sine is cosecant x. So that would be my whole thing simplified as far as I can for the first half. Now on the other side, this one's a little bit easier following our rules, and so if I remember that cosecant, if I ask you to take the derivative of cosecant x and cotangent x, then cosecant x, when I take the derivative of it, turns into a negative cosecant x, cotangent x, and cotangent turns into a negative cosecant squared x. So if you look now, I pretty much have the same thing. I just have my signs. Well, since I was already subtracting and this one should have been negative, it would turn into a positive. And so now my y prime, if I just reorder it, cosecant squared x minus cosecant x cotangent x, and that's the same thing that I have down below. And so that's what we proved them, and that's what we're looking for. So moving along, so then these are all the examples that we've done and just the different ways of simplifying them and getting them down to their answers. I just wanted to show you that how you started them. These were the steps after you differentiated what they should look like, and then how I simplified them. And it's just a reminder of what we're going on. And then we want to talk about higher order derivatives, and there are an infinite amount of derivatives you can take. The first derivative has the name of velocity. The second derivative has the name acceleration. The third derivative has the name jerk, and then there's a name for fourth, fifth, and sixth, and so on and so forth. And we'll talk more about these things in class, what they are. But what I want you to get across to you is look at all the different notations. There's 5 different notations for everything, and you need to know all these different notations. You need to kind of just be familiar with them, because you don't know how they're going to ask for it on the AP test and or my tests. So you need to make sure you're familiar with those different notations. So then our final example for today is basically finding acceleration due to gravity. And so basically we're given this, we're saying that because the moon has no atmosphere, I'm going to let you guys kind of read through it. Here is our position function that is given to us. So what we need to do is to find the acceleration, we need to do the derivative twice. And so that's what we're going to do. And so we're going to say s of t is our position function, and we get negative 0.8 t squared plus 2. If I take the derivative of this, this will give me velocity, which is negative 1.62 t. This is velocity. And then if I take the derivative again, which is negative 1.62, this is acceleration, which is really what we're looking for. And so since the acceleration due to gravity on the moon is negative 1.62 meters, this is meters per second squared, and the Earth is negative 9.8 meters per second, if we want to figure out how the Earth and the moon are related, we're going to say negative 9.8, which is the Earth, divided by negative 1.62, and when we divide those, we get approximately 6 as our ratio for our gravitational, the Earth to the moon. And so thank you for listening, and this concludes section 2.3.